member of the German Research Foundation Special Research Group 533 on sauropods, which looked at all aspects of their life in order to find out what allowed their gigantic size. And a large part of that turned out to be biomechanical stuff. And so this is the first thing we will talk about today. You can see on the screen a size chart for some of the largest or longest animals that ever lived on land. And you will notice that they're all sauropods. Why is that? Well, if we look at a size chart of dinosaurs, of biggest dinosaurs, you see they're all pretty big. Sauropods dwarf them. And compared to mammals, let me put it this way, they're just 10 times bigger or more, at least an order of magnitude. So even the body of Diplodocus, which is not a very big dinosaur, but has a very long tail, and that makes it a very long dinosaur, a very long sauropod. The body is several times bigger than the biggest known African elephant today. So sauropods with their trunk volume are in the range of whales, not the biggest whales, but normally aquatic animals. They're way outside anything we see in big mammals today, with the exception of elephants. There are some smaller sauropods the size of elephants, but an order of magnitude bigger. So when you look at here, Argentinosaurus 33 meters, don't believe these exact numbers. Many of these finds are from quite incomplete individuals, but still Diplodocus is really well known. And you can see the size comparison to a human here on the left of the screen. You can almost walk upright under the belly of all these animals. Try that with an elephant, it doesn't work. These are huge. So one of the most interesting questions obviously is, how did they work at that body size? I mean, you have to move that body, you have to feed it, you have to heat and cool it, you have to reproduce. How do you do all that? And the other interesting question really is, how did they get there? If we look at their ancestors, here is one that I love very much, Platosaurus engelhardti from southwestern Germany. That is already a pretty impressive dinosaur at almost 6 meters length. But how did these guys become these guys? Here is probably the most famous skeletal mound of a sauropod in the world. This is Giraffa Titan branchi in Berlin. Used to be Brachiosaurus branchi, and it is the largest, the tallest mound of a sauropod in the world from real elements. Although I should say that the neck are copies for a reason that plays into biomechanics, because the neck vertebrae are so fragile and so thin that they couldn't be mounted without putting too much metal on them, and then people wouldn't be able to see that. So Janensch decided not to mount them, but mount plaster models. Today they are fiberglass models. So these two questions, how did they work and how did they get there? They're obviously intertwined. Because all the intermediate stages also had to work in some way. So let's talk first a bit about how the ancestors worked. The fairly basal sauropodomorphs like Platosaurus, Lufengosaurus, Moosaurus, there's many more. These lived at the end of the Triassic, the beginning of the Jurassic, and that was basically the time when dinosaurs suddenly got big and suddenly got dominant. What do they look like? They're fairly basic dinosaurs. They're bipedal. You will see old mounds of Platosaurus as a quadruped. If you have the chance, go close, take a good look at how the bones are articulated and have a good laugh. One of the things that you can see here, they have radius and ulna as they should be. The radius is on the radial condyle and the ulna is on the ulnar condyle. Can you actually see my mouse, Octavio, Francisco? Could someone tell me if I move the pointer, it should show. Does it show?
Hard to see.
I'm moving it on the left arm now. Do you see anything?
No, we still see the Giraffa Titan mount.
Okay, this is weird. I'm sorry, this is really weird.
I think you need to share the screen instead of the window.
I did in the beginning. Does it now show Platosaurus?
It does.
Yes.
Okay, I'm sorry. Very quickly, let me show you.
We do see your mouse. Now I can see the mouse. But the mouse is small and sometimes it's hard to put.
Okay, I'll try moving it in circles to make it better.
It's a tiny one.
Okay, let me quickly try to make it bigger. Here, just for a second. This is annoying because all that has been adapted on my... Is this better?
I guess.
You should, okay. You should now see a sauropod size comparison and a big, big, big pointer.
It's not a big pointer, but it's better, I think.
Yes.
Okay. It should be big and yellow.
I can confirm yellow. But fine, let's carry on.
Okay, good. So anyways, when you look at the Platosaurus skeleton here, you can see that the radius is on the radial condyle of the humerus and the ulna is on the ulnar condyle, and that's where it's supposed to be. And if you go to the quadrupedal mounts, you will find that these bones have been exchanged. And obviously, you can try it with your own hand. If you flip the elbow 180 degrees, it flips your hand. And that's how they get the palm of the hand to show downwards to the ground. Is not a mistake a paleontologist should make. Cough, cough. So anyways, what do we see? We see a bipedal animal. It has, on the hind feet, it has long toes. It has a fairly long metatarsus. Then it has a long fibula and a long tibia. And then it has a long but curved S-shaped femur. So the normal limb posture we can see from the curvature, which helps against bending, is in a zigzag posture as we see it in almost all land animals today, with the exception of stupid humans and stupid elephants. Elephants have changed that for the same reason sauropods have. We will talk about that later. Humans, we are just weird. So forget about humans. It's to do with tree climbing. Okay, so we see a zigzag limb posture. You can also see that in this mount. This is the other mount in tubing, and you see that the knee is in front of the hip, and then the ankle is back, and the animal is digitigrade. So it's supported by its toes and not by the whole flat foot. It then has a long tail. And you see it has very long hemal arches under it. And this is the attachment for the large caudofemoral musculature that pulls to the femur and brings the entire leg back. We see a fairly compact trunk, and then we see a long neck with a small skull. These are all basal dinosaurian characteristics, actually. Obviously, the neck plus skull length is adapted so that the animal can reach the ground while standing. That's important. If you are a small animal and there's predators around, you don't want to sit down to eat or drink from the ground. You want to be flight ready. So we see this correlation here. Interestingly, we also see that in mammals today. Think of herbivorous mammals, cows, sheep, horses, etc. They can all eat from the ground while standing for the same reason. They just have bigger skulls in some cases, and so they have proportionally a shorter neck. One of the very few exceptions, giraffes can't drink from the ground without going into a special pose, which is risky and which is what gets them killed. But giraffes are extreme, longest necks in mammals. Okay, we see here a typical animal adapted. It can move speedily. That is indicated by the long distal leg. Although you see more of that in mammals, one of the reasons is that you can see here in the ankle, there is no tuber calcaneae that increases the moment arm of the shank muscles. So what for us is important, the Achilles tendon going into the muscles, allowing jumping by extending the ankle. These guys were not good at that. Also, you see a bit of a crista here. So the front of the tibia is pulled outward a bit. That increases the moment arm of the muscles coming from the thigh, and that helps extending the knee. Again, that's good for running and jumping. But also, these animals are adapted for long, slow walking, and that has to do with the fact that they are herbivorous. Plants contain much less energy per volume than animals. So if you eat animals, a carnivore needs to eat a lesser volume of food compared to a herbivorous animal. So the herbivore, if it gets bigger, needs to be able to move around slowly to find all the plants to eat. And because plants typically don't run from you, they don't need to be able to run quickly to hunt plants. No, the plant just stands there and you can eat it. So you see an adaptation to walking long distances in these animals. And that is the overall fairly long leg and a fairly long femur with a strong muscle pulling the entire leg backwards. That's what you do when you walk. You move your entire leg backwards and your body moves forward as a consequence. The interesting thing is that there is now very ample evidence that Plateosaurus already was a warm-blooded, very active animal with a bird-like lung. We do see postcranial pneumaticity in the neck of some individuals. That means that air sacs that are not in the skull, but in the neck, have invaded the bone to reduce weight in places where bone isn't needed structurally. We also see a rib cage with certain angles between the ribs from which I calculated the air exchange volume of the lungs. So how much air goes in and out when the animal breathes. I compared that to other animals today, and I compared it to the estimated body weight. And it turns out for mammals, this ratio between tidal volume of the lung, how much air goes in and out, and body weight is fairly constant. It's 5.7 milliliters per kilogram or something like that. And for reptiles, and especially for birds, it varies enormously, and the values go up into the 90s or even hundreds. So they can bring in a lot more oxygen per breath. Now remember, bird lungs also use twice as much of the oxygen in the air, so they're way, way, way more efficient in getting oxygen in. That's because they have a very high metabolism. Interestingly, the lung of Plateosaurus, tidal volume versus body weight, plots with geese. This is the giant goose. So very active animals, moving around a lot, air sacs in the body. That is an important key when we want to understand sauropods. But a fairly typical zigzag limb posture, bipedal, balanced, with the center of mass, it's about at the end of the pubis over the foot, okay? We can see here, this is one of the best finds from Trossingen. We see that the animal died in a resting posture, the limb fully folded up and back, the front limbs are at odd angles, an indication that this was not a quadrupedal animal supporting itself. And we see a fairly narrow body and a narrow hip, again, typically dinosaurian. The tail is missing in this specimen. So this is, I call them the cows of the late Triassic. Size, weight wise, they're comparable to cows, big cows. Okay, so how do we go from there to an animal like this? You can see sauropods are quadrupedal, in this case with very long forelimbs, or in the case of Dicraeosaurus in the background, a shorter forelimb. They still have the big tail, but there is one noticeable difference. I think I have open here somewhere a nice image of a sauropod foot. Oh, well, let's just take this one. This is a sauropod foot, and you can notice immediately that compared to Platosaurus, the toes are practically gone. There is one claw left, and it's on the first toe, and the second and the third and the fourth toes, remember, they were long and supported the animal in Platosaurus. You can see it here. You see here, these are toes 2, 3, and 4, and the foot is symmetrical. And you see here, there is almost nothing left. The next thing is that in proportion to the animal, the metatarsus is short. And also, it's not a symmetrical foot with the first and the fifth toe very short, actually almost absent in Platosaurus. It is a symmetrical thing with a big claw stuck on the inside, a number 1. So metatarsus looks symmetrical, but there's this big claw. Now, one important thing that happened here, and that's evidence we have from tracks, is also that under all this metatarsus, there was a big pad of connective tissue. So what has happened here is that the foot has become much shorter, the toes have reduced massively, and this thing is more shaped like a big stamp than a foot with mobile, flexible toes. And that is an adaptation we also see in elephant. It is an adaptation to weight bearing. That's the first difference. The second difference we see, remember that the femur in Platosaurus has this curvature, and its cross-section here in the middle is fairly round. Now, both of these indicate that typically the femur was held in an inclined position, so it experienced bending along its long axis, and the round cross-section and the S-shape help taking that up. If we look now at Giraffa Titan, we see two differences. One of them is that the femur doesn't show the curvature anymore. That's gone. And the other one is that when you take a cross-section here, in the middle of the shaft, it's actually much broader, the aspect we see it here, than it is thick. So it's not round anymore, and it's not as curved anymore. That's an indication that this extreme bending moment is gone. The next thing is that the distal facet isn't pointing slightly backwards. We can see it here if this is the long axis, and then we draw a line for this articulation. There is an angle between them. That's not the case in sauropods, they actually have straight femora and the distal end points in a straight line. And the crista linealis in the tibia is really, really small. So what we see here is a limb that is no longer zigzag. It is straight. And that means, and the shortening of the distal elements, that these animals were totally unable to run. There is simply not enough force to extend this leg to make a jump or to run. Rather, the leg is, we call it, pillar-like or columnar. That is excellent for weight bearing. And we see it again in, ta-da, elephants, as always. However, let's imagine you are an animal the size of Platosaurus, and you get bigger, and you get so big that you have to straighten your limb to be able to carry your weight. That will get you into problems. One of the problems is that the center of mass is somewhere here in front of the pubis, but your support point is under the hip. With a zigzag limb, you can put your foot under the center of mass and you're balanced. Let me check very quickly if I can find the file I want, and I will show you a nice side view of how Platosaurus is balanced. Now, if you move the foot back under the hip in a straight line, then obviously your center of mass is in front of where you would need it, and you will fall flat on your face trying just to stand. That's not a good idea. Now, what can you do about this? One option would be to shift the center of mass backwards. Now let's imagine you're an animal like this, and your center of mass is in the hip, and you pull your leg backwards. What happens? Your body tilts up. And the predator chasing you says, oh great, my prey stands still. I can kill it easily. How nice. Bad idea. What you actually want is a center of mass that's in front of your point of support when you want it, so that gravity will help you accelerate forward. The other thing is, if you stand there just like a T, a vertical strut, and then a big, big bar across, the slightest imbalance will tilt you forward or backward. You will fall on your face or on your ass. With a zigzag limb, that's not a problem, because you can balance easily by just bending your ankles and knees and your hip a tiny bit or straightening it a tiny bit. That's a system that allows easy dynamic control. If you have a vertical leg like that, imagine we humans, we have a vertical body. So we don't have these big moment arms. So we can balance easily on our straight limbs, but now carry something heavy and you start leaning back and forth, and if it gets really heavy, what you start doing is actually bending your legs a bit so you can balance better, for the very same reason. Let's see if this has loaded. Yes, it has. Okay, with the big mouse, this is a bit. So here you have a Platosaurus skeleton posed with its maximum stride length, and I can put in a little blob where the center of mass would be. It's about there. And you can see that with the zigzag limb, if I put it into a standing pose very quickly, it's not a big problem to get your toe under your center of mass. I can't really handle this well with the big mouse pointer. Okay, and then you have this big, so I can, oh geez. This is a vertical, and you see this line, there's a good support here. With a straight limb, let me fake a straight limb, a sauropod-like limb here. When we go like this, and then like this, And you see that the center of mass is way in front of the foot. And also you can see this big T I talked about. So we have this big bar and the support is like this. And now if I start tilting this in any way, if I start doing, this, can you see the motion? And normally you just flex your limb a little more and that doesn't work. Okay, so what can we do in this point? Well, one of the things you can do is that you have this T here and you just add a little support here. What happens if this starts tilting? If this starts doing this? Well, every time it tries going down in front, pop, it has to stop because your strut in the front supports it. So these wild oscillations, they don't happen. Well, congratulations, we have just invented the quadruped. Now, how does that look in sauropods? We can look at this one, or we can maybe better look. Typical example. If we look at, I need a skeleton. I want a good side view. We can take this one. Scott Hartman always delivers. So here we go. What we see is that we have this basic dinosaur body plan with a long neck, a compact trunk, a long tail, and we have this new adapted vertical hind limb with a small foot, and the forelimb is much shorter. Look at where the shoulder joint is compared to the hip joint. But it reaches the ground and it can serve as a stop to body oscillations. That is a key thing. If you start going big, you have to straighten your hind limbs at 6 or 8 tons or something. And now you need an added support. However, that is a big influence on life. In Platosaurus, the hands are free to manipulate food. We think they may have scratched, digged for the subterraneous shoots of equiseeds and other plants. They lived in a complicated environment, partly flooded during parts of the year, desert rest of the year, short vegetation period in between. So they were adept at finding food in difficult environments and digging it out. If you have a support function here, it's hard to also have a hand that can do complex motions and grasp things. So you're losing capability in procuring food. The other thing is you lose the ability to run and jump as you straighten the hind limb, and the front limb doesn't really help. Running with the front legs alone doesn't really get you anywhere. So these quickly also become pillar-like. We see again a compact hand, and then we see a bit more zigzag in the pose, and we see a bit more here of an olecranon process than tibial crest. Apatosaurus is the most muscular sauropod that's well known, by the way. So in many others, it looks weaker. We also see one other thing, however, that immediately happens. Notice how long the neck is? That neck is way longer than is needed to reach the ground. So what is this big neck for that these animals start developing the moment they become quadrupedal? Well, it's about feeding volume. It's about having a big, heavy trunk and losing the ability to dig for food easily and all that. Well, with a big neck, a long neck, you can move your small skull around in a big volume and eat a lot of plant material that's there. I think there was a nice figure. I had this in the, here we go. That's one of the results from our research group. If we look at feeding volume, what amount of plant matter can a sauropod reach with its neck compared to other animals? And you can see that the long neck gives them a huge sphere, semi-sphere they can reach. And this is assuming a fairly stiff neck. So the body doesn't have to move. And that saves a lot of energy. And it also allows you to reach higher up. Another advantage sauropods have is that in most of them, the center of mass is fairly far backwards. Here is a typical example in Barosaurus or Diplodocus. And you see that they can tilt their body up, add their body length to the neck length, and bam, they can feed high up in trees that without sauropods around would be safe from being eaten. Interestingly, Giraffa Titan doesn't work well because you can see that the hip joint and the center of mass are far apart. So the X is the hip joint and the white dot is the center of mass. So this is a badly balanced animal. This is a well-balanced animal. You can see that elephants are in between. So these guys could stand upright a lot better than elephants today, with the exception of brachiosaurids and similarly shaped sauropods. So the long neck gives enormous feeding range, but you're expending little energy to get your skull to where the food is. Interestingly, as sauropods get bigger and bigger, their skulls don't. So the skull of Diplodocus is almost the size of the skull of Platosaurus. Why is that? Because if you have a bigger skull, then you're moving a big skull around on that long neck. And that has a big moment arm. It makes the motions slow and it costs energy to do that. We see here a system of transporting a small light skull to the plant matter. As a direct consequence, you can't have big teeth and you can't chew. If you want to chew plant matter, you need big teeth. If you need big teeth, you need a big skull. That means a strong neck. And if that is very long, then you have this big weight hanging in front. And that's energetically nonsense. And also, if you move your neck quickly, then you have a large moment of inertia. And that gets you banging your skull into trees all the time. Not a good idea. So, while these animals have a skull of a small to normal size for their body size, if you want to get huge, as sauropods do, you cannot increase your skull size much. The biggest sauropod skulls are maybe twice as long as Platosaurus. That's all there is. And that directly means you see all these teeth here in the skull of Platosaurus. These are teeth adapted at crunching up tough plant matter. These guys can also bite through small bones with them. Actually, we find a lot of isolated Platosaurus teeth around Platosaurus finds, and it looks like scavenging. So these are fairly omnivorous animals with a preference for plants, probably, and they can deliver quite a bite. If you look at sauropods, geez, I mean, their skulls are just tiny compared. And look at other dinosaurs. We do have other dinosaurs like Stegosaurus with really tiny skulls, but hadrosaurs have big skulls. Theropods have fairly big skulls, and ceratopsians have huge skulls. These guys, not so much. So what is the secret how this goes together? Sauropods lose the ability to bite down to a level where they can just strip some soft matter, some plant matter off a thin branch, or in the more sturdy skulls like Canterosaurus, they can bite off thin twigs. Thin twigs. That's it. But they can get in a lot of volume. We're talking about a cubic meter of plant matter per day. That's a lot. And because their bodies are so huge, if we look at these animals, it becomes clear what happens. They actually have a huge trunk in which they can have long intestines. And the interesting thing is that if you put food through a short intestine, it comes out with the poop containing most of the energy that was in the food. So you're using a low percentage. And the bigger you get, the longer it will take for the food to pass through. And the longer it takes, the more of the energy can you take out. And sauropods are big enough that it doesn't matter how the food goes in the front end, chewed or not chewed, small bits, big bits. It is in the intestine long enough to break it down completely and get all the energy out. So a mouse poops out 90% of the energy it eats. A sauropod, maybe 10%. So here, changes in locomotion, making the limb vertical and going quadrupedal, and changes as a result in neck length mean changes in physiology and how food is processed in the body. Becoming big, becoming quadrupedal, opens up new food resources in the tops of trees, or very efficient grazing. There was no grass then, but other small plants. But at the same time, it means that you must be huge, because otherwise you can't process this food sufficiently. On the one hand, an advantage, it opens a new niche you can grow into. On the other hand, you're stuck in that niche. We do see some very small sauropods develop from big ones, but they're all island dwarfs. And you know, small islands, competition isn't what it would be in a big continent normally. So on the one hand, this combination of factors allows them to get big, and on the other hand, it's a one-way street. You specialize into this niche and there is no getting out. Once you have made your feet just small weight supporters that can cushion and impact well, once you've straightened your limbs, it's very hard to go back to speedy running ability. Because when you just shrink your body size, everybody outruns you. Not a good idea. But you need to shrink first before you can go back to a zigzag limb and long toes and all these things. So it's a one-way street and it's opening up new niches, and then you hit the next barrier. You hit barriers in sauropods of heat. As your body gets bigger, the volume gets bigger by the cube, but your surface area goes up by the square. That means that your metabolism produces heat. If you're small, you can easily lose it through your skin. And as you get bigger, you heat up more and more. You need special structures to get rid of all the heat. That was one of the main arguments people brought why sauropods had to be ectothermic animals. They couldn't be endothermic, homeothermic, producing their own heat and controlling it, because they would overheat and all stroke. Well, there is one interesting thing how you can increase your surface area without changing your external appearance. And that is very simple. We have here a nice figure produced by Mike Taylor. If you don't know his blog, he has this blog together with Matt Weddell, who is also someone you should know. Sauropod vertebra picture of the week. Lots of interesting information there. Do go and read it. Here is a figure he made of the fifth neck vertebra of Giraffa Titan. And you can see that this vertebra has enormous pre-zygapophysis and has a lot of these thin bone thingies here, flat areas of bone, and you see a lot of holes, indentations. These are the product of pneumaticity, and that is that air sacs in the neck have basically excavated the bone and have made these hollows in places where the bone is not structurally needed. But the big moment arms here, transverse processes down to the ribs, the moment arms for the muscles stay the same. So the same structure contains air instead of muscles, fat, or bone, but has the same strength and has the same power for much less weight. And it also means that there is new cooling area, because you can actually just put blood vessels around these air sacs, give the heat off to that air, and then exchange the air as you breathe. Bam! So your heating problem is solved, and at the same time, the same pneumaticity makes your neck lighter, which allows for the same weight a longer neck, which allows for a bigger feeding range. Win-win all around. On the other hand, it makes your neck very, very, very fragile. So you don't want to get bitten in it. But hey, if you're so big and tall as a grown sauropod, then the risk of getting bitten in the neck is fairly low. Most predators just can't get up there. Now you may notice there is a problem with this, because it's nice to see animals this size and say, oh, they're almost safe from attack. But they have to grow there. They have to grow into this size. And there is a limit to the size an egg can have. The embryo in the egg has to breathe. It has to get oxygen in and get CO2 out. And if an eggshell becomes too thick, it can't do that. The embryo will die. So the thickness of an eggshell is limited. And as an egg gets bigger, the curvature of the shell becomes less. And for a given strength, it at a certain point becomes too unstable. It will crack. That's at about 5 liters. So you can't have a hatchling animal that weighs more than 5 kilograms. Now we're talking about animals that weigh 10, 20, 30, 40 tons. And they grow from animals that weigh 5 kilograms at most. So what's going to happen? There's going to be these tiny sauropods around with their stilt-like, their columnar limbs. They can't run, so they move slow. That's meals on stilts for all kinds of predators. 99.99% of baby sauropods get eaten before they grow to a size where they can defend themselves with tail lashes or kicks against predators. Sounds like a problem, doesn't it? Well, actually, I just said that pneumaticity allows sauropods to be bigger and stronger per weight than they would be without. It also allows them to control their excess heat from a high metabolism. And that high metabolism allows fast growth. So actually, the time that they're exposed to this high predation pressure is fairly short. They probably grew to their full size, not as we used to think in hundreds of years, but in a decade or two. Their growth was enormous. The other thing is that this wouldn't work at all for mammals, although mammals grow very quickly. But think of the size of a mouse at birth, of a lamb, or a piglet, a horse, a foal, and then think of a baby rhino or a baby elephant. In mammals, there is a correlation between the size of the newborn and the size of the mother animal. Why is that? Because in all mammals practically, the baby has to be able to move with the mother or the herd. You know, it's a bit tough to feed a young animal with milk if the animal is not where the mother is. So the baby, if the mother gets bigger, the baby needs to get bigger, much bigger. As a consequence, the rate of birth goes down. Tiny mammals have young 2 or 3 times a year, rodents. Bigger animals have one every year. Elephants, every 6 to 8 years. As you can see, the fertility of the species goes down with size. As a consequence, the few offsprings you have become such a big investment that even more is invested in them to bring them up. That is why you find in big animals all these case strategies, few offspring, and a lot of investment in volume, just volume at birth, and in care for the young. Think of how long elephants stay with their mothers. Now there's a size limit. Why? If you imagine animals as big as elephants or bigger with their low number of offspring, and then some catastrophe happens, a meteorite impact, a new viral illness, a new contact with a different continent brings in different predators, different germs, whatever, and you kill off most of the population. How quickly will it recover? Well, one calf every 6 years. Well, maybe every 4 years, and their survival rate is going to go up. But the recovery rate of big mammals is low, really low. And that's why in conservation, people are so worried about big species like panda bears, rhinos, and so on. Let's imagine the same thing for sauropods with their 5 kilo offsprings. How many eggs can a sauropod lay every year for the same investment in energy as an elephant having a calf? Dozens to hundreds. Okay, as I said, 99.9% of these get eaten. But if a catastrophe happens, if almost all the population dies out, then all the predators also almost die out. So the survival rate will go up, and in elephants that may mean that twice as many babies survive to adulthood. In sauropods, it will mean that hundreds suddenly survive. And that means that their recovery rate of the population is enormously high. Now we see we have this mix of traits. I kept saying they have the long neck and the big tail and pneumaticity. We see that in basal dinosaurs. The egg laying, that's basal dinosaurs. So they have some very conservative traits. And on the other hand, they have new innovations like the elongated neck, like shifting from biting food much to fermenting it in the trunk. And this mix is unique in sauropods. And this mix, not one part alone, only this mix of characteristics actually allows them to get to giant size, and it locks them in giant size. They can't easily get out, which is why we have so few dwarf sauropods only in very specialized circumstances. Okay, this is basically what I think one should generally know about sauropod mechanics and evolution and how it interplays with other aspects of their biology. Octavio, are you happy at this point? Should we shift quickly to Stegosaurus?
Yes, I'm happy. I mean, the audience is yours.
Okay.
You decide.
You all take a 2-minute break. I'll bring up some pictures to show you on Stegosaurus.
Okay. And meanwhile, you can see Francisco mounting a stegosaur in real time. Really well done, Francisco.
I actually... Oh yeah, now I see it. Nice. No, I can't see what I want to see. Okay, that's good. Oh, there it is. And why am I actually... Why am I actually so stupid and don't just go to my own paper? Okay. So there we go. And should be a figure here. Did I put that video online? Now I hope this paper has... Come on. Oh, it's the freaking PDF. I don't want the PDF. Mm-hmm. Okay, I didn't include the video I wanted to include. Okay, everybody, let's talk a bit about Stegosaurus. I'll keep this to the one I know most about, and I'll just point out how it is still a generalized dinosaur, and then we'll talk about my exact research on it, which is just on the aspect of how they defended themselves. And I'll mention an interesting thing to note on this specific skeleton and some of the bones. And then maybe you can look at yours. And I know that the Portuguese material has interesting similar stuff. Okay, very basically, we have our typical dinosaur in that it is an animal that has a long tail, a fairly compact trunk, long neck, tiny skull. It's an archosaur and all that. In this case, a quadruped. And as you can see, interestingly, again, we have a columnar hind limb, so a very straight femur. However, it's not flattened as we've seen in sauropods, where we see this to the extreme in the humeri of Brachiosaurus and in the femora of Brachiosaurus. This is still round. There's a reason for this. We see, like in sauropods, convergently, a much reduced hand and a much reduced foot, actually way more reduced than in sauropods. And then we see something that we don't see in sauropods at all, which is, however, common in ornithischian dinosaurs. We see bones in the skin and different types. Here, Kentosaurus doesn't have ossicles on the throat, but it has plates and spikes along the neck. This one on the shoulder, I disagree with that. I think this goes on the hip, as Henning originally put it in Kentosaurus. Yes, there's Gigantospinosaurus with a shoulder spike from China, but that spike looks totally different. The plate it attaches with is totally different. It fits the scapula. This plate here actually fits the hip. You see the upturned rim here? You see this rim? This is actually where the longissimus dorsi muscle goes under. Okay, having said that, we all know that typical Stegosaurus in classical paleontology, that's Stegosaurus from the US, and it has big plates on the back. And there's been a lot of debate on what they're for. Are they for display? Are they for heat loss? Are they armor? Could they be, as Backer suggested, fold left and right to defend against attackers, etc., etc., etc. One advice for the less experienced student here: single cause explanations are typically not correct. Typically, what you have is several causes. Once the structure is there, once it's there for maybe heat loss, why not make it colorful and make it also a display structure? Okay, Canterosaurus got me interested for a number of reasons. One was that I walked by this skeleton every day. Another one is that I unofficially helped in remounting this. And the third one is that I used to work with a modeling software that allowed kinetic dynamic modeling, which means that it didn't just take the motion of objects into account, but also their mass and inertia. Now, in a lot of motion, inertia plays an important role. For example, in walking, the swing of your legs and of your arms plays an important role. But where inertia gets really interesting is if you have systems with many tiny components that move together, and then inertia is transferred to an ever smaller part of it, a whip. And people have been suggesting that the tails of Stegosaurus with their spikes at the end, here is a nice example from Stegosaurus itself, spikes at the end, that they were used as a defensive or offensive weapon, that Stegosaurus would whack others with these spikes. Kent Carpenter did a lot of work on that and found that a lot of these spikes are actually broken and healed. And he also found that there was a suspicious number of fibulae in Allosaurus that were broken at just the height they would impact. And also there is a famous example published by him and some co-authors of a pathological Allosaurus vertebra. And there's numerous pathologies on this vertebra, and actually there's holes through it, and you can take one of those spikes and stick it just through those holes. There's also a callus on it, so the animal started to heal after the injury. So at least in one case, a Stegosaurus whacked one of those spikes deep enough into an Allosaurus to probably kill it. Slowly, painfully. This arrangement of spikes at the end of the tail of a stegosaur is called a thagomizer, after this wonderful Gary Larson comic. Now this end is called the thagomizer after the late Thag Simmons. But is that actually true? Was this one find of the smashed up Allosaurus vertebra just a freak accident? Was there enough mobility in these tails? And was there enough power in these tails to actually use the tail tip as a weapon? So what I did in my paper, I made a 3D model based on the skeleton of the Canterosaurus in Berlin because we had high-resolution 3D scans of it. And you can see that I put these spikes at the very, very, very end of the tail. Sadly, there are a few vertebrae missing here. Otherwise, it's one complete individual. Why did I do that? Because there is actually a wonderful find in the Berlin collection. This is the tail tip of a Canterosaurus. And you can actually see that these vertebrae are the size of about my thumbnail. So the tips were at the very, very end. They had these spikes. What I also did is I reconstructed the tail musculature. And that was one of the things where I really pissed off a bunch of the paleontological establishment. Because what I did is I looked at a lot of stuff that people were writing. And what they did is they drew an ellipse around the outline of the bone and put muscles in. And that was supposed to be how you reconstruct tail muscles in a dinosaur. Well, I looked at crocodilians, and I looked at iguanas, and I looked at other animals, and I found, if you look here, this is a cross-section through the tail of an alligator, and you can see here the caudofemoralis muscle and the iliocaudales, ischiocaudales, and so on. And you can see here, first of all, this is where the bone ends. This is where the bone ends. The other transverse process isn't hit. And this is where the humeral arch comes out. And the muscles go way beyond the bone. And I produced this figure where on the right, I did what people did to reconstruct dinosaurs. And on the left, I traced reality. And you can see that these muscles get a much, much bigger cross-section. Much bigger. But not only that. The black points indicate the center of these cross-sections. And from here to here, for example, is the moment arm of this muscle for moving the tail sideways. And as you can see, the real moment arm is quite a bit bigger than the reconstructed one. The white one is for all muscles for the sideways aspect. And you can see that it almost doubles. So one thing I noticed in the course of this research is that tail muscles in most dinosaurs that were reconstructed were way too small, way too thin. Is that a problem? Well, let's say you make them half as big as they should be. As a consequence, they're half as powerful. So you might think that your estimate of walking speed or impact of the tail or something is half. No, it isn't. Because you're calculating half the force times half the moment arm. You multiply your error. So what you get is a quarter of the real value. You're making them a quarter as strong as they were. That's a big problem with a lot of research into biomechanics. If you underestimate the muscles and underestimate the moment arms, then you're messing up big time. It's not so much true if you model limbs, because the tendons go across the joints fairly independent of the size of the muscle. If you make a bigger belly for the muscle, the tendon doesn't change course much. But in the tail, there is a lot of change. So I did several reconstructions of Kentosaurus. I did the conservative one that I knew was probably too low. And I did one where I used the fattest alligator I could find. And I used an intermediate one between the two. This is too little. This is probably way too much. This is probably close to the truth. And then I created a life model of the animal that was sectioned into discrete units. And between them, I could move, you can see here, this is the model of the tail with one segment for one vertebra. And I could now make the software move the joints. I'm sorry, I don't know why my Acrobat is acting up and jumping around. I could make this model move each joint with the torques I had calculated for the joint from the moment arms and the muscle thickness. And I quickly ran into computational problems. You see that these are very many segments. And so the software said, yeah, I can run that simulation, but it's going to take 3 months. Whoopsie. And you see here in gray, I've overlaid this detailed model. You can see tiny red points here if you look at the paper. It's online free at Paleontology Electronica. You see the joints are the red points. So I made a simpler model with just 5 sections that produced nearly the same curvature and had the same volumes and weights. And it was this simplified model, you can see it here, that I used to make this tail swing. So what I did is, I first looked at the motion range of the tail. This is just with the bones. I moved each bone to the side so that the zygapophyses still overlapped a bit. Sometimes people say they retain 50% overlap. Kent Stevens does that in his sauropod neck analysis, and golly, the animals are stiff, very, very stiff. Well, I looked at a lot of extant animals, so did Andreas Christian and Gordon Dembski and others, and there is way more mobility than Kent Stevens assumes. Here I retained a bit of overlap between the zygapophyses, and I looked at resting pose in iguanas and in crocodiles and in all kinds of animals with long tails, and they all can do this motion. Actually here, this is if I only allow 2 degrees of motion per joint. This is 5 degrees and this is 6. Why do I get such an enormous curvature? Because there's so many elements. If you have 20 joints times 5 degrees, you're already 100 degrees off your original course. So now I took my simplified model with the few sections and I made it swing through this arc in the software that takes into account the acceleration and the mass and everything. And I made a simple superimposed plot here, and it shows you the position from the start and then at 5, 10, 15, 20, 30, and 42 meters per second. So the tail tip reaches 5, 10, 15, 20, 30 meters per second, and here 42. This is a model assuming the realistic muscle and a realistic force per square centimeter for the muscle. This one's also in the realistic range, and you can see it tops out at 58 meters per second. And then there are models. This is the huge tail, the fat tail, and assuming very high force per muscle cross section, and it tops 100 meters per second. I think that's unrealistic. This is way too high. Similarly, if you go to a model that takes the weak tail and the weak muscles, then I think you're underestimating. But actually, I think this one is it. This is the Croc model. So this was the strong model. And I did an analysis of the medium model where we get 40 to 50 meters per second. Again, discarded the strongest. And this is the weak tail. And here I discarded the weak tail with weak muscles. But even that, 28 meters per second, 40 meters per second, depending on the strength of the tail. To be conservative, I always discounted the strongest muscle version. So 20 Newton per square centimeter, 39, 50, and 78. There are actually a lot of papers out there who find values in the 60 to 80 Newton per square centimeter for certain muscles. So that's not a crazy value. I'm still discounting it. And if we then look at the results, we get consistently impact forces over 3,800 Newton per square centimeter at slow speeds, and then it goes up to values in the 10,000s. And for comparison, I put this in. If you look at the failure parameters of the frontal region of the human skull, so how much force does it take to crush your forehead, which is strong bone, you know? It's around 5,000 Newton per square centimeter for a thin spike tip. And that means 20 to 25 meters per second. The models all call that. So Canterosaurus was easily able to crush your skull with a good hit. I discussed all these things in detail. Read it if you want. But one interesting thing here is that came out. What really kills, you can see it in these graphs here. What really kills is not just the speed increase at the end, where the whiplash action comes into play here, but we're already getting 20 meters per second in this arc behind the animal, depending on the reconstruction. So from here to here, the animal hits you, you're in deep trouble. Okay? Another thing that I noticed when I looked at the mobility of the skeleton here for the tail, well, I did the same thing also for the neck. And even a conservative reconstruction, you can see here, brings the eye to the side of the body. So the animal can just look left or right and can see what is behind it. But even more interesting, and I hope I find this picture quickly, the neck is actually long enough. This is what a friend of mine, an artist, did. If you look at this picture here, actually the neck is long enough that if the animal lifts the skull all the way up, it can look backwards over its own back. Here it has a 360-degree view. So having the tail to defend the posterior quarter and a good view means that approaching the animal from behind was high risk. You can see the look. So good. My research showed that Canterosaurus could easily defend itself against attacks from behind. The thagomizer was a thagomizer, but what about attacks from the front? If we look at this here, look at that neck. It has some plates on it, so maybe biting into it is not a good idea for small animals. But for something the size of an allosaur, and we know allosaurids of that size were around in the Tendaguru Formation where this comes from, easy peasy, just crush the skull, just kill this animal easy. Well, this is where the columnar legs come into play. And look at this forelimb. Look how big the humerus is, how massive. And then you see here on the ulna, a huge olecranon. Here comes the interesting tidbit. This olecranon is, by the way, purely cartilage. We have ulnae. Let me show you. I think it is in one of these papers. It's idiotically in my Platosaurus paper, but here you have a digital version of the ulna you just saw on the skeleton in the mound. And this is two other ulnae, also of Kentosaurus. And you see this massive difference in shape here. And you see here, it's like a cap is stuck onto it. And this here is stuck onto it. In this individual, for some reason, the articular cartilage that was fibrous ossified. And you see the cartilage here, and you see it here. Now this is an ulna that indicates a very strong elbow extending musculature with a big moment arm. This, much less so. So be careful with dinosaurs. If you're lacking the cartilage, you may misinterpret their motion range and their actions. But in any case, we have here the ability to extend this elbow very forcefully, and we have a very strong shoulder. And we have, at this end, a columnar limb. And you can see how the arm can be abducted and then folded down. What does that mean? It basically just means that if Kentosaurus spotted an attacker in the front, it could very easily push sideways with the front limbs and spin around on the hind limbs and have the tail face the attacker. So this is basically the way how they got their thagomizer to face the attacker, and by putting their neck up, they could keep the attacker in view. That's what I did on Stegosaurs. There are a lot of other interesting topics on them, on their mechanics, etc., but I don't really know too much about them. So I'll finish this lecture here and hope it was interesting for you. Are there any?
Well, thank you so much. Now I think it's time for questions.